Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the digital circuits. Today in this video, we are going to talk about the number representation. As of now, we all know what is a number system and how we represent the different number system in the different radix, right? So we all know what is a binary number system, octal number system, hexadecimal number system and the decimal number system. But till now we have discussed all of the number system which are positive only, right? We have just talked about the positive numbers. But what about the negative numbers? Can the computer be dealing with the positive or the negative sign? No, computer don't understand positive and the negative sign. So how to represent the negative numbers? If I have a negative number and a positive number, this type of number is known as a signed number, right? So we have a sign associated with a number and the computer does not recognize this sign. So what we do, we put a digit which is a sign bit. With the sign bit is going to denote what sign the number is having, right? If I have a positive number, it is denoted by a positive sign bit, and if I have a negative number, it is denoted by a negative sign bit. So today in this video, we are going to talk about the sign number representation, then the complementary number representation of the sign numbers, and then we are going to talk about the floating point number, right? So we are going to talk about a lot of important topics, and this video is going to be the base of the upcoming video. So this video you should understand very deeply. So first of all, what are the sign numbers? Sign numbers are the number which are having the positive or the negative sign associated with it. Like if I have plus 5 or if I have minus 5, I have to denote the sign with 5. So it will be denoting the signed number. It cannot be represented by the positive and the negative sign inside the computer, right? So computer don't represent it the number with the positive or the negative sign. So what does computer do? Computer represents sign number with bits only, and we are denoting the sign number with the signed bit. So this is the sign bit which is going to represent the positive or the negative number. How we differentiate plus 5 or minus 5 inside a computer? It depends upon the sign bit. Sign bit is going to differentiate between plus 5 and the minus 5. So if I have a positive number, sign bit will be equal to 0 if I am talking about the computers or the binary number system, right? So in binary number system, sign bit we directly put 0 if it is a positive number. So if I have plus 5 and if I have the 5 bit number, so 5 for 5 bit, I will be representing this as my sign bit. Okay, so before the MSB we will be having the sign bit. The leftmost digit will be the sign bit, and then I will be representing 5. 5 is represented as 101, and because it's a 5-bit number, here we will be putting 0. Okay, now if I have a negative number, for the negative number the sign bit is equal to 1, and again this is for the binary number system. If I have the different octal or decimal number system, I will be having the different sign bit. It will not be represented by the one sign bit, right? So if I am dealing with the binary number system, like if I have minus 5 in the binary, how it will be represented? Minus 5 will be represented with the most left bit to be equal to 1. I told you in the binary the sign bit is 1 if it is negative. So here we will be having 1. Then 0, 101. 101 represents 5 and this one represents the minus sign. So if I have any number with positive or negative sign, and the digits of the number can be represented as a n minus 1 up to a naught dot a minus 1, a minus 2 up to a minus m, and the radix is r, right? So if I am talking about any general number system with any radix r, so it can be represented with this. If I remove this positive or negative sign, I will be using a sign bit, right? So sign bit and the number as it is, a n minus 1 up to a naught dot a minus 1, a minus 2 up to a minus m, and this representation when I am using a sign bit is represented with this subscript RSM, which means the base R and the sign magnitude representation. SM represents the sign magnitude, right? So the positive number will be having S is equal to 0. Again, like in the binary, if I take any number system, the positive number system will be having the sign bit equal to 0 in any r, right? But if I have the negative number, the sign bit will be equal to r minus 1. For example, if I have minus 5 in the decimal number system, minus 5 can be represented as 9, 10, right? So this can be represented, as 9, 5. Okay, so this is represented in the 10 number system or the decimal number system. So decimal number system, here we have, instead of r we will be placing 10, and SM represents the sign magnitude. So 9 represent over here r minus 1, which is 10 minus 1 for decimal, and 5 was the actual magnitude. Okay, similarly if I have minus 5 in the octal number system, so here we will be having r minus 1, which is 7, 5, which is the magnitude, and here we will be having r as 8 and sign magnitude representation. So if I give you any r, if I give you any number, it could be positive or negative, you can now represent it. If I have plus 5 in the base, let's suppose 6, so it can be represented as 0 because it's a plus 5 number. So the sign bit will be 0, the magnitude is 5, so 6 SM. This is how I can represent any positive or any negative number in any base. Okay, now coming to the complementary representation. As of now, we have represented the given number's magnitude as it is. If the number is something, the number is 5, I have represented is binary equivalent, which is 101. But now we can have the other representations of the given number as well. We can have the complementary representations. We can have 2's complementary representation or the 1's complementary representation as well. We are going to talk about the 2's and the 1's complementary representation in the upcoming video as well. As of now, I am going to give you the introduction to the 2's and the 1's complement. If I have the positive number, we will be using the binary magnitude and we will be having the 0 sign bit. This magnitude will be the same magnitude that we have for the given number, right? We are not going to have its complement. In the negative number, we are going to take the magnitude as 2's or the 1's complement. So instead of 101 as 5, I will be taking the 2's complement of 101 or 1's complement of 101 to represent the negative number, and we will be having the sign bit equal to 1. Okay, so because it's a negative number, sign bit will be equal to 1. So for example, if I have minus 51, if I want to denote it in the sign magnitude form, so minus 51 will be having this bit as the sign bit and all of these bits are the magnitude bit. 110011 represents 51, so this is the sign magnitude representation in the binary, so we can represent it as 2SM. Okay, so now here we have the 2's complement form. In the 2's complement form, minus 51 can be represented as the 2's complement of this number. In the next video, we are going to talk about how to convert this number into its 2's complement. So as of now, understand that all of the ones I am converting to zeros, all of the zeros I am converting into 1. So I have 1 1 0 0 1 1, what it will be. So if I convert 1 to 0 and 0 to 1, it will be this, right? And then I will add 1 to it. So if I add 1 to it, so last 0 is converted to 1, and over here we will be having 0 0 1 1 0 1 as the 2's complement. Okay, 0 0 1 1 0 1 is my 2's complement, and because it has the minus sign, here the sign bit is 1. All of the magnitude bits are this, right? So it can be represented as now as a 2's complement representation, right? So we represent it as 2CNS. Okay, so here we will be writing 2 as well. 2CNS. This is the subscript that we use to represent the 2's complement form. Then we have the 1's complement form. Again we have minus 51. So because here we have minus, sign bit will be 1 and here the subscript will be 1CNS. And how to convert the 1's complement? All of the 1's are converted to 0, all of the 0's are converted to 1. So 1 here is converted to 0, 1 converted to 0, 0, 1, 0, 1, 1, 0, 1, 0. And this is how we will be getting the 1's complement representation. Don't worry, we are going to talk in detail about the 1's and 2's complement in the upcoming video. So what is the basic formula to find out the r's complement? If this is the case for the binary number, but if I have any radix r, r's complement or the radix complement can be found out as n dash r. This is the r's complement number. It will be equal to r raised to the power n minus n r. So this is the given number that we have. If I subtract the given number from r raised to power n, we will be getting the r's complement. If I have the given number, I can convert it into the r's complement with the help of this formula. Now the positive full scale will be equal to r raised to power n minus 1 and the negative full scale will be equal to minus r raised to power n minus 1, right? So this is how we will be getting this minus 1 is over here. Okay, so in the power we will be having minus 1. So now coming to the r's minus 1's complement. Okay, so for r's minus 1's complement, we represent it with n double dash subscript r minus 1, and it is the same number, r's complement minus 1. So r raised to power n minus n r minus 1. This is how we will be getting r's minus 1's complement, which is called the diminished radix complement. Now if I have the 8-bit number, the 8-bit number will be having the range from 0 to 255 if it is an unsigned number, right? So 2 raised to power 8 minus 1 will be the maximum number which can be represented by 8-bit if it is unsigned. But if it is a signed number, because first bit we are using as a signed bit, we will be having the range from 127 to minus 128, right? So range is reduced if I am using a signed bit representation. Now if I have a 16-bit computer, because mostly we are dealing with the 16-bit computers, so it will be having 16-bit word length, and the range would be 2 raised to power 15 minus 1 to minus 2 raised to power 15 minus 1, right? So the maximum number it can be storing, as if I have a 16-bit computer, what is the maximum number a single register can be storing? A single register can be storing maximum up to 32767 number. If I have a number greater than this, I will be requiring 2 registers to store this number. Okay, if I have a least number which is minus 32767, it can be stored in one single register of 16-bit computer. If I have a number which is even lesser than this, it will be requiring 2 registers. So the double precision is the precision where we are requiring the 2 registers to store the larger numbers. If the number is beyond this range, we will be requiring the 2 registers, right, for a larger number representation. In the triple precision, I require 3 registers to store even a larger number. Now coming to the floating point numbers. I hope you understood how we represent any signed number with the signed magnitude representation, with 1's complement representation, with the 2's complement representation. Now if I have a very big or very small number, we represent this number with the exponent representation. Okay, very large and very small number. If I have 10 raised to power 50, if I have 10 raised to power 100, so how do I represent this number? With the help of the exponent. If I have the decimal number, so in the decimal number, how I can represent the floating point number? With the 10 raised to power. So it is represented in the exponent of 10. So we can represent any number as 10 raised to power. So 6.6 into 10 raised to power minus 34, it's a decimal floating point number. Then we have the binary floating point number. It is represented in the power of 2 or exponent of 2, like 1.1 into 2 raised to power 11. So this is the binary number system. So how we are representing any floating point number? We are representing it in the form of m multiplied with r raised to power e. Here r is the radix, like for the decimal I had the base 10, for the binary I had the 2. So r represents here the radix. What is m? M represents mantissa and e represents exponent, right? So any number over here can be represented like this. So if I have any number plus minus a n minus 1 up to a naught dot a minus 1 up to a minus m, so this is a basic number that we have in any of the radix r. So this number can be represented as plus minus dot a n minus 1 up to a minus m in the base r multiplied with r raised to power n. Now here what would be the mantissa? This part would be my mantissa and this would be my n will be my exponent, right? So this is how we can represent any floating point number. Now how do I represent this sign? Because here I will be having this sign as well. The sign is represented by the mantissa. Okay, so sign is represented with the mantissa only, and this part is the mantissa. So with this part I will be using a sign bit. Okay, so you have to see the mantissa, you have to put the sign bit with the mantissa. So Sn dot an minus 1 up to a minus m in the sign bit magnitude representation of the base r. So here if I talk about m is sign bit representation with the magnitude. S is the sign bit which is placed with the mantissa. Okay, but if I talk about E is the exponent which is coded in the excess k form, right? So we will be talking about the excess 3 notation in the upcoming video. So whatever E we have, we are coding it. We are not using the exponent directly. We are using it in the excess k form. Now k here is used as a bias. It is called as a bias, and it will be having the value 2 raised to power n minus 1, where n is the total number of bits in the given number, right? So how many bits I need to represent the given number in? It is n. So here E is coded in the excess k in the 2's complement form, and if I talk about the bias number, it can be represented as minus 2 raised to power e minus 1 less than equal to d less than equal to 2 raised to power e minus 1. Now what I will be doing, I will be taking this minus 2 this side, so we will be having 0 less than equal to d plus 2 raised to power e minus 1 less than equal to 2 raised to power e. So now in the excess k form, the exponent is represented. It will be having the range this, and the excess k form exponent will be represented in the form of this. So a subscript e minus 1, a subscript e minus 2 up to a naught. This is my exponent representation. Okay, and this the uppermost digit is representing the sign bit. So exponent will also be having a sign, because here we have 10 raised to power minus, here we have 2 raised to power plus. Where this sign is represented? This sign is represented in the most significant bit of the exponent, right? And the exponent is excess k coded. Okay, so I hope you understood how we are representing the floating point number. So the given number will be having the mantissa and the exponent. So now if I represent the given number, it will be having Sn ae minus 1, ae minus 2 up to a naught, and an minus 1 up to a minus m in r. So this is the given representation of the floating point number. So how do I make it in a graphical form? So single precision format is represented as Sn, which is the sign bit, then the exponent, and then the mantissa. This is the given representation in the single precision form. If I have extended precision, right, if I have double or the triple precision, so we will be having the sign, exponent, mantissa, which is having the most significant part, then the mantissa, the least significant part. Sign and exponent will be having only one sign and the one exponent for a given number. Obviously, if I have a given number, if it is a bigger number, if I want to represent this bigger number with the 2 registers, then also this power would be 1 only. 10 raised to power would be 1 only, so we will be having only one exponent, and the sign would be 1 only, so we will be representing it one sign only. But the registers are 2, the mantissa part is stored in the 2 registers. Coming to the computer format, how a computer is going to store the number, because the computers are dealing with a very big and the very small numbers, they are going to store the number in the floating point representation, and this is the reason we were talking about the floating point number. So the mantissa will be occupying the 10 bits and the exponent will be occupying the 6 bits in the computer. Okay, 10 bits are reserved for the mantissa, 6 bits are reserved for the exponent, and the mantissa is always in the 2's complement form, in which the most significant bit is representing the sign bit. Okay, in the exponent we are using the excess 32 notation, and if I have the negative exponent, obviously. Now the mantissa, it's an example, and the mantissa is given as plus 0.101000000, and the exponent is also given, which is 1000011. Because here we have the exponent to be this. How do I found out the actual exponent? Actual exponent will be this exponent minus the 32 number, and 32 number will be represented as 100000, right? So this is the 32 number. The most significant bit was 1, and this is how I got to know that I have to subtract the 32. So 32 is subtracted from the given number. I will be getting 4011. So now what is the number that is left out? So we have over here mantissa as plus 0.1010 base 2 into 2 raised to power. This is the exponent. So exponent is 4011, which is the 3. Okay, so 2 raised to power 3. Okay, it was a binary number, so we have taken the power of 2. I hope you understood all of the things that I have discussed in this video. If you have any doubt about any of the topic, you can put the doubt in the comment and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, share it with your friends, and also give me your feedback. Thank you so much.